Hello friends, welcome today's lecture Flexibility Method. Myself Mr. Y. S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yadgaon. So in this lecture we solve a fixed beam problem by using flexibility method. So this is the first statically indeterminate structure. That is a fixed beam AB having a UDL of 20 kilonewton per meter at a span that AC is equal to 3 meter, and the total span of this fixed beam is 5 meter. So degree of static indeterminacy is 4 minus 2, that is number of unknowns is 4, means reaction at A, reaction at B, moment at A, moment at B. So at A support 2 unknowns, at B support 2 unknowns. So 2 plus 2 is equal to 4, and number of equilibrium equation used in this problem is 2, that is summation Fy is equal to 0 and summation M is equal to 0. There is no horizontal force in this system, so there is no need to use horizontal, that is equilibrium condition, that is summation Fx is equal to 0. That's why the degree of statical indeterminacy becomes 4 minus 2, so that value is 2. This structure is statical indeterminacy is 2. So convert, now I want to assume the redundant forces. So in this case we assume the redundant force is RB and MB, means when this is the RB and this is the MB, moment at B, this is the redundant force. Remove these two redundants. Now when I remove these two redundants, that vertical force and moment, the structure becomes cantilever structure, and the cantilever structure is a determinant structure. So redundant forces are that RB and MB. So form a matrix of redundant forces, that is R matrix. So R matrix becomes the redundant force. This is nothing but RB and MB. This is the redundant matrix. Then displacement analysis of released structure. When I remove the support at B, the structure becomes cantilever structure subjected to UDL over a span of AC of 20 kilonewton per meter UDL intensity. So I can easily find out, or I can easily solve this problem. This is a determinant structure. So this diagram called as M diagram. Then next I want to apply redundant force on the free structure, that is RB, at support or at point B. That unit is 1 kilonewton unit load, that is M1 diagram. Similar way I apply redundant force, that is MB, at point B. Intensity of the moment is 1, that is M2 diagram. So by using this M diagram, M1 diagram and M2 diagram, form a table. First portion BC, in between B to C, origin is B. So M moment in between B to C, there is no load, that's why M means moment in the M diagram is 0. Then next M1, see here M1 diagram, there is a load between C to B, that is 1 kilonewton, and direction with respect to B, that moment is 1 into X, measures this X distance measures from point B. So direction of the moment is clockwise and left side clockwise is plus, that is 1 into X, so become X. Then M2, the M2, see here M2 diagram, due to this 1 kilonewton moment, the direction of the moment is anti-clockwise, on the right side anti-clockwise moment is plus 1. So this is M2 is 1, and the limits in for that BC portion is B to C, that is measures from B origin, so 0 to at point at C is equal to 2. So limits become 0 to 2. Then next for portion CA, this is a A, not B. CA. Now CA, once again consider origin B. Now on the CA portion there is a UDL. What is the intensity moment with respect to B due to that UDL? That is 20 is the intensity of the UDL, where it is at half of the distance. What is the distance? x minus 2. X minus 2. So that equation becomes minus 10 x square minus 4x plus 4. Then once again for that M1 diagram, so M1 diagram on that, due to this RB that redundant force is 1, so it becomes x. Similar way for that M2 diagram, the moment become 1, so this is become M2 is equal to 1. And now limits are C to B, means we measures from origin is B. From B, what is the distance of C is 2, and what is the distance of A is 5. So limits is 2 to 5. Next, displacement analysis of released structure subjected to loads corresponding to redundant action. So form a DRL matrix. For DRL matrix, we want to calculate DRL1. For DRL1 is equal to M into M1 dx upon EI. So M value for first condition is 0. So 0 into x becomes 0. There is no need to consider this condition. Then second is M into M1. First, that M is minus 10 x square minus 4x plus 4. This is M into M1 is x. So multiply by x. So solving this equation, we got that minus 10 upon EI x raised to 4 divided by 4 minus 4x raised to 4 divided by 3 plus 4x squared by 2, and the limits are 2 to 5. So putting this upper limit and lower limit, simplifying this equation, we got minus 382.5 upon EI. Then next DRL2. So it becomes M into M2. Once again, M value for that BC portion is 0 into M2 1. So 0 into 1, 0. Then next is minus 10 x square minus 4x plus 4 into 1 with limits are 2 to 5. By simplifying or taking integration, the equation becomes minus 10 upon EI x cube by 3 minus 4x square by 2 plus 4x with upper limit is 5 and lower limit is 2. By putting this upper limit and lower limit values in this equation, we got DRL2 is equal to minus 90 upon EI. This is the DRL matrix. Then next, form a flexibility matrix by using this table. Suppose now this matrix will be 2 by 2 matrix. So we want to calculate first F11. How to calculate F11 is equal to integration of M1 into M1 dx upon EI. So M1 value is x. For that BC portion, so 1 upon EI integration of 0 to 2. This is the first limit into x, that is x square dx, plus for that BC portion, sorry, that AC. For that AC portion is x into x, that is x square dx, but limits are changed, that is 2 to 5. So put up 0 to integration of 0 to 2 x square dx plus integration of 2 to 5 x square dx. By solving this equation, we got F11 value becomes 41.67 upon EI. Then next F12 and F21 value are, both value are same, is equal to integration of M1 into M2 dx upon EI. So first M1 is x, M2 is 1 for that BC portion, and the limits are 0 to 2. So 1 into x become x into dx, limits are 0 to 2 x into dx, plus for that CA portion, once again M1 is x, M2 is 1, but limits are 2 to 5. So 1 into x, x into dx, limits are 2 to 5. Solving this equation, we get F12 and F21 value is 12.5 upon EI. Then next, form F22 matrix. For F22, integration of M2 into M2 dx upon EI. So 1 upon EI, M2 for that BC is 1. 1 into 1, it is 1, but limits are 0 to 2 for that BC portion. So 0 to 2 integration 1 dx, plus for CA portion is M2 becomes 1 into 1, that is 1 dx, and the limits are 2 to 5. By solving this equation, we got F22 is equal to 5 upon EI. The flexibility matrix become F1 upon EI, take constant, take outside of the bracket. The F11 is 41.62, F12 is 12.5, F1221 is 12.5 and F22 is 5. This is the flexibility matrix. So general compatibility equation is dr is equal to drl plus f into r. So dr is equal to displacement matrix is 0. So drl is 1 upon EI minus 382.5 and minus 19 plus 1 upon EI 41.67, 12.5, 12.5 and 5. And redundant matrix is RB and MB. So RB into 41.67, MB into 12.5 is equal to minus 382.5. Then RB into 12.5, MB into 5 is equal to 90. By solving these two simultaneous equation, unknowns are 2, that is RB and MB. We get RB is equal to 15.12 kilonewton upward direction and MB is minus 12.78, that is hogging, means negative. Then by using this RB and MB, we calculate bending moment values. So already we know the bending moment at B is minus 19.78 kilonewton meter. Then bending moment at C, I want to find out bending moment at C, taking moment about C. So 19.78, that is clockwise, right side clockwise, consider minus plus 15.11 into 2. So bending moment at C value is 10.44 kilonewton meter. Then bending moment at A, taking moment about A, that is 19.78 minus plus 15.11 into 5, this is A to C distance, minus 20 into 3 into 1.5. So bending moment at A is minus 34.23 kilonewton meter. So draw this diagram first. At A is minus 34.23, negative value plot downside. At B 19.78 plot downside, and at C is 10.44. So join all points. Okay, then next shear force calculation. Shear summation V is equal to 0. RA becomes RA minus the total number of forces in the vertical directions are 4. That is 3. That is 2 reactions and 1 UDL. That is RA minus 20 into 3 plus 15.11 is equal to 0. So RA becomes 44.89 kilonewton. So shear force at A becomes 44.89. Then shear force at C is 44.89 minus 60, that is minus 15.11 kilonewton. Then shear force at B is minus 15.11 kilonewton. So plot points. Shear force at A is 44.89, shear force at B minus 15.11, so drop downside. Shear force at C is minus 15.11, so join line. So there is a shear force diagram cuts with the baseline. Suppose this is the point D. So this is a zero shear force. So I want to calculate this distance. How to calculate the distance? That shear force at A is 44.89 minus 20 into X. So X becomes 2.24 from point A. This is the distance. So bend that at where the shear force is 0, the bending moment is maximum. So I want to calculate maximum bending moment. So maximum bending moment is equal to minus 34.23. This is the moment at A plus 44.89 into 2.24. This is RA into that distance 2.24 minus 20 into 2.24 square divided by 2. That is 2 into X square divided by 2. That X become 2.24. The maximum bending moment is 16.15 kilonewton meter. Put up this 16.15 kilonewton at point D and join all the points. Above the baseline the values are positive, below the baseline the values are negative. So this is a solution for a fixed beam carrying partial UDL on the span by using flexibility method. And Next, how to calculate the point of contrafracture values? Equal that there are 2 points of contrafracture, means that bending moment also cuts the baseline. So I want to calculate distance first for portion BC. In this condition, at this is the bending moment at this point is 0. So 15.11, consider this is x. 15.11 minus 19.78 is equal to 0. There is no load. So 15.11 is a RB into x and directly minus 19.78. So x becomes 1.31. Then portion AC, means in this condition total number of forces are 3, that is RA, MA and partial UDL. So first 44.89 into x, then directly minus moment, that is MA moment 34.23 minus 20 into x and x by 2, that is 20 x square by 2 is equal to 0. So it becomes, equation is x square minus 4.49 x plus 3.42. Solving this equation, we got x is equal to 0.97. This is the total solutions for a beam, fixed beam carrying a partial UDL by flexibility method. Thank you.